All right, hey everybody. We're going to look at homework from 7.2. We're doing hypothesis testing. And hypothesis tests, you remember there are three kinds. There are left tail tests, right tail tests, and two tail tests. So I've picked three problems which do one of each. And so I'm going to go ahead and start with number 2 here. And these early problems are kind of nice because they walk you through the steps basically, and there's a lot to this. So we'll go ahead and start reading. It says to conduct a hypothesis test for a population proportion P, we have to determine null and alternative hypotheses first. The alternative hypothesis is one of the following. We do little h1, and then you have to do one of these. Either P is bigger than a value, P is less than a value, or P is not equal to a value. And you determine that based on just reading the problem. So we'll do that in a second. Then the null hypothesis is always H0 P equals a value. And you would use the same value here that you used up here in the alternative hypothesis. And then H1 actually determines the type of test that you're doing. So when H1 says P is bigger than a value, that's a right tail test. Bigger than points to the right. Okay, when H1 says P is less than a value, that's pointing to the left, so you're going to do a left tail test. Okay, and for not equal, that technically means greater or less, so either tail works. It's a two-tail test. Okay, so those are the three kinds of tests. So when you read this problem here, it says we got a sample size of 212. I'll just be making notes as we go. 106 successes were observed. Test the claim at 5% significance. That's our alpha 0.05. That the population proportion of successes is less than 50%. Less than 57%, that's an alternative hypothesis. P is less than 0.57. And with the null hypothesis, right, so it's a less. With the null hypothesis, we just change it to an equals. P equals 0.57. Now, at some point, we're going to need Q here. Q is always 1 minus P. So we'll go ahead and do 1 minus 0.57. And so this is our Q value, 0.43. Okay. We'll need a P hat value, X over N. So I'll go ahead and do that real quick. 106 divided by 212, that's your sample proportion. Okay, so that comes out to be exactly 50%. Normally, we would round that to 3 significant digits, but this one doesn't need to be rounded. It's just 50%. Okay, and then let's go ahead and just put in what we've got here. So the null hypothesis should say P equals 0.57. I'll just type that in. And the alternative should be P is less than 0.57. Okay, and then because this points to the left, we know that when it points to the left, we're doing a left tail test. So we'll go ahead and say here that this is a left tail test, and we'll check the answer. So everything looks good so far. Okay. Now, the next thing we would do is the check. So the criteria for approximate normality are, as previously, NP has to be greater than or equal to 10, and NQ has to be greater than or equal to 10. The value of P to be used is from the null hypothesis. So our null hypothesis, we assume that the population proportion is 57%. Q would be the complement, so that was 43%. And so we use those to check NP and NQ. So again, N was 212. So we're going to do 212 N times P, which is 0.57. Okay, so we'll do that over here. Okay, so that comes out to be 120.84. And then NQ 212 times, I think we got a 0.43 for that. So we'll do that real quick. Okay, so that's 91.16. Remember, we require that both of these are at least 10 in length. That's the left tail and the right tail of the binomial distribution. Those need to be at least 10 in length to get the symmetry we need to use a normal approximation on that. So we can go ahead and put these values in here to the homework. So this NP 120.84 that looks good. NQ 91.16, and yes, these are both greater than or equal to 10. So I guess I usually put little check marks down here for both of those. I'll go ahead and say yes here and check the answer. So just double back, everything looks great. Okay, so next we need this test statistic. So this is just to see how many standard deviations our sample proportion of 50% is below what we're assuming, and that's 57%. We are claiming the population proportion is less than 57%. We got 50%, that seems less. Let's see how many standard deviations below. So that's the next computation, and we can go ahead and put in our p-hat value here. This was a 0.50. Normally I would do that to 3 significant figures as it says, but I actually didn't round that at all. Okay, so now let's do this Z test statistic. TS for test statistic. Okay, formula is p-hat minus p over the square root of PQ over N. All right, so the p-hat was 0.50. Again, normally 3 significant figures there. Minus p, 0.57. Okay, and down below, over the square root of p, that's 0.57. Times Q, which came out to 0.43 over N. So N was 212. Okay, so let's work that out here. .5 is the same as 500. You don't have to put all those digits in. Minus 0.57 over square root fraction inside p is 0.57 times q 0.43 over n 212. Okay, fingers crossed here. So this one they want you generally to 2 places. We're going to have to go with negative 2.06. So that seems significant. Remember, 2 standard deviations below is roughly our rule for statistical significance. We got 2.06 here, and the 50% is a little more than 2 standard deviations below 57%. That's usually beyond the margin for error, but we need to look a little more closely based on the level of significance here. So let's go ahead and just put in what we've got, negative 2.06. There, and check it. Okay, so that's good. Now it says there's 2 ways to determine if the difference between the sample proportion, that's the p-hat value of 50%, and the assumed population proportion of 57% to see if the difference is statistically significant, either using a critical value, which is a z-score from the bottom of table A2, or using a p-value, which is the probability of being at least as extreme as our z statistic, which was the negative 2.06. Okay, so we can look up the critical value on table A2 under the column with the appropriate alpha, 1 or 2 tails as appropriate in the bottom row. So the critical value is made negative if it's a left tail test, okay? And whenever the test statistic is beyond the critical value into the appropriate tail, then it is statistically significant. And so let's go ahead, put in our level of significance here. It was 0.05. Okay, and now we need our critical value. So this is where we're going to pop over to table A2. Just notice this is a left tail test here. So that's just one tail, not two. And so we're going to pop over to that table real quick. It's right here. Okay. Remember our alpha is 0.05, so we can circle that wherever it is, but it's a one tail test this time. Okay, and then all the z statistics are down in the bottom row. So I'm just going to kind of slide all the way down here to 1.645. That's going to be our z critical value. So let me go ahead and put that down here. I'll just type it in 1.645. But let's go ahead and draw a little picture to support that. So this is CV for critical value. Okay, we go, maybe we just start with a little picture of this. Okay, because it's a left tail test, we're going to put this on the left of 0. So we're going to have to make it negative. Okay. When you go to table A2, we ignore degrees of freedom and just go to the bottom row where it says large. Those are where the z-scores are. Okay. Our alpha, again, 0.05. One tail. And when you do that, come down, and I believe it said 1.645. Okay, but remember, this is a left tail test, so the critical value, we need to make this negative. Negative 1.645. Okay, so that's our negative z critical value. All right. And so I just want to put in the correct value over here. I put in a 1.645 here, but it should be negative. It's a left tail test. So let me just change that to a negative. And then we can decide if our test statistic here is statistically significant. So what you want to do there is just kind of plot this point. What I'm going to do is shade the tail here. This little tail that starts at the critical value, okay, I want to go ahead and plot where my negative 2.06 is. It's going to be over here in the distribution. So we're putting the negative 2.06 just right here. Like that. And that does look statistically significant because if it's in the tail, we can conclude that it is significant. Statistically significant, to be a little more precise. So I'll go ahead and put that in. Yes, the statistic indicates the sample proportion is significantly less than the assumed population proportion. Okay, so we're all good here. Okay, so next thing here is we need to work on our p-value. So here it says we use table A1 to determine p-values for z statistics. On a right-tailed test, the p-value is the area to the right of the test statistic. But remember, we're doing a left-tailed test. So on a left-tailed test, the p-value is the area to the left of the z test statistic. And on a two-tailed test, the p-value is twice the area to the right of a positive test statistic or to the left of a negative test statistic, right? So we're doing a left-tailed test here, and we need the area to the left of our z test statistic. That's for the p-value. So I think we go down a little bit here and just kind of maybe make one more diagram. And I'll go ahead and put it right here. I think I want it to be a different color. And let's put our test statistic down. So the test statistic was negative 2.06. So I'm going to go out kind of far in the tail here. So negative 2.06 was our z test statistic. And this area here is going to be our p-value. Okay, and so we just have to look that up in table A1. So let's grab that table. Oops. So we just kind of go for a z-score down to negative 2.06. Okay, like that. And let's see what it says. So real quickly, I'm going to bring that table up here. And we'll just highlight it here, negative 2.0, 0.06. And so looks like we have a 0.0197 there. So I'll go ahead and set that up here. 0.0197. Okay, and let me go ahead and label this on my little chart, my little diagram here. 0.0197 is our p-value. That's the area to the left. I think I'll even shade that just because. Okay, and we can put our p-value in here. Like that. And that's pretty small. Looks like we got it right. It's less than 5%. So that means we have statistical significance. Okay. Remember, it has to be less than the alpha value. And if you go back up here, our alpha value here was 0.05. And the p-value is closer to 0.0197. That's 0.02 really. So 2% versus 5%, it's less, which makes it statistically significant. Now we're going to basically draw in this little diagram that creates the p-value. So the test statistics negative 2.06, we just want to dial that in here on the left. So negative 2.0, where are you? 456, right there. And you can see the p-value 0.0197, which is what we got. And this little red line here is the critical value, which was the negative 1.645. And so whenever the test statistic goes into this little tail, starting at the critical value, we have statistical significance, but also then the blue region here, the p-value, will be a smaller region than the pink region, which is the level of significance, your alpha value. So clearly the p-value will be less than alpha whenever that statistic goes into the tail. Okay, let me go ahead and submit that. And now the bottom line is, and the rule here is that whenever the p-value is less than the level of significance, we reject the null hypothesis and support the alternative. So again, our p-value is at 0.01. Let me put this down here. P-val is 0.01, and then I'm going to kind of put in the 97 very faintly, because we only really need to think about the first two digits when we compare it to alpha. 0.01 is definitely less than 0.05, which is our alpha value, I think up here. Yes. And whenever it's less, that means we reject the null hypothesis. And the point of rejecting the null hypothesis, and that is sort of the goal, when you reject it, then you get to support the alternative. Okay, so here, because the p-value is less than alpha, we reject the null hypothesis and support the alternative. So just clicking on that, that's all you have to do on this one. We don't have to write out a conclusion here, because there's not really a context to this problem. So we'll just leave it at that. Okay, so next I thought we should take a look at problem number 5. So let's pop over there. All right, because this one doesn't give any instructions. So any of these problems that have a context to them will not have instructions, and so you hopefully by the time you get to question 5 or whatever, you're kind of to the point where you kind of understand what's going on. So you should just kind of pay attention and realize you're going to need to learn how to do this without help. Okay, so it says in a survey of 113 randomly selected Apple Macintosh users, 68 identified themselves as politically liberal. So let me record this. The N here is 113, and of them 68 considered themselves liberal. And it says tested claim that a majority of Mac users are politically liberal, and our alpha is going to be 0.05 again. Okay, politically liberal. All right, well, since I'm here, I'll go ahead and do my p-hat value. So this will be 68 over 113. And again, we'll do 3 significant figures here. So let's do that real quick. All right, so that's 0.602, I guess we'll go with. Okay, and then for the null hypothesis and alternative hypothesis, it says here that a majority of Mac users are politically liberal. And a majority just means more than 50%. So for the alternative hypothesis, we're saying that more than 50% is the proportion of Mac users who are politically liberal. And that means in the null hypothesis, we'll say that P is just equal to 0.50. And notice this H1 here is pointing to the right. Okay, so to the right means a right-tailed test. So we'll just make that note. Okay, so we'll go ahead and put this in here, right-tailed test. HO said P is 0.50. P for the alternative is greater than 0.50. So that should be okay. Majority. Now we do this check with the NP and the NQ. So for P, well, we better do Q. Q is 1 minus P, and for P we're using 50%, so the complement of that will also be 50%. Okay, so NP would be 113 times 0.50. Q is the same, so it'll also be 113 times 0.50. So these will be the same. So I can do that over here. Like that. So it's 56.5 on both of them. And recognizing these are supposed to be at least 10 for that bell-shaped distribution on the binomial distribution that allows us to use a normal approximation. So both of these are 56.5. And yes, the criteria are satisfied, both of them being greater than or equal to 10. Okay, now we already did our sample proportion. Up here it was 0.602, so I can put that in. And I'll check it, so we're good. Then we need to do our z-statistic. So down here, we're just going to put our p-hat value in, which was the 0.602. For p, we're going to use 50%, which is what is assumed to be true in the null hypothesis. So we can go ahead and put in these. So 0.602 minus 0.50 on top, and then down below, square root of PQ. P and Q are both 0.50, so we're going to have a 0.5 times a 0.5. You don't need that 0 there afterwards. It's just for looks, I think. Okay, over n, which is 113. Okay, and then it says to round it to 2 places, so we can go ahead and do that real quick here. All right, so 0.602 minus 0.5 to see how many standard deviations this is from 50%. We're claiming it's more than 50%, so we do have something that's more, but I don't know, that might be within the margin for error. Okay, and then divided by the square root with a fraction, 0.5 times 0.5 over n, that's 113. Okay, and so we're going to go with 2 places, 2.17 here. And let's just check that real quick. Okay, looks great. All right, now we're going to start working on the critical value and then the p-value after that. So first it wants the level of significance. So you can see over here we wrote down 5% for that. So that's a 0.05. Okay, and then we need our z critical value. This one's a right tail test, so our critical value is going to be on the right side. So I'm going to go first of all to table A2 to get the critical value. And we just put in our alpha here. It's 0.05. And remember, this is a right tail test, so we just look it up under one tail. Okay. And so let me just pop up. I think we've done this before, but I'll just do it real quickly here. 0.05 one tail. So the 0.05 one tail is this column here, and it's all the way down to the bottom row. And we've seen this number before here, 1.645. Okay, that's our z critical value, and we'll keep it positive because it's a right tail test. Okay, so let me just pop over there real quick, and maybe we can add to our picture here. So 1.645 is what we got, It's a right tail test, so I'll put this to the right of 0 and not make it negative. Again, that's the Z critical value, little subscript CV like that. Okay, and that's all we have to do here. We'll just put it in. 1.645. Now, this whole issue of statistical significance is just determining if that test statistic here made it into the tail, which I'll shade real quick. So here's the tail. I'm shading it, starting at 1.645. The area of that tail is alpha, which was 0.05. Okay, and then the 2.17 here, I'll put a little dot here. It's to the right of 1.645. Okay, so it's in the tail. Which makes it significant. I don't want to write that there. Hang on. So it's like, I want to put this on here. I don't know where. So I'm going to put it next to my arrow. So this one's in the tail. Which makes it significant. Okay. And that's all I got room for. And so the question here, I haven't checked anything, but it did make it to the tail. It is significant, so we'll go ahead and say yes. It's significantly greater than, the 602 is significantly greater than 50%. So that seems to support the alternative hypothesis. If I could just click this thing, it's not clicking, there we go. Okay, and now the p-value. Okay. So for the p-value, we're trying to find the area to the right of 2.17. So you go to the little normal distribution again, put down the test statistic 2.17. That's the Z test statistic. Okay, and we need the area to the right of that. So I'm going to shade that in, and that'll be our p-value. Oops. Okay, so we'll figure that out. If we look up 2.17, now this is table A1, so we're going to go down to the 2.1. Just trying to make my colors right. 2.1 and then over to 0.07 to make 2.17 in table A1. Remember, this will give the area to the left of 2.17, but this is a right tail test, so we've got to be careful. So let's go ahead and just get this real quick. So 2.1 and 0.07 like that. So that's 0.9850. So that's what we're seeing in the table here. So I'm going to bring this back. So in the table, as I say, it's 0.9850. That's the area to the left. Okay, that's not what we want. It's a right tail test, so we've got to squeeze in 1 minus 0.9850, okay, to get our p-value. So that I'll do that over here on the calculator. Okay, so that's 0.015. I'll end it with a 0 if they want 4 places. Maybe I'll put a 0 at the end. But 0.015, so basically 1.5 percentage points is what we've got there. So I'll go ahead and denote that down here. That p-value is 0.015. 1. And then I usually like to kind of ignore the last 2 digits when I compare that to alpha. So for the moment, they want all 4 places right here. So 0.015, and then I'll add a 0 just for good looks. Okay, and that should be fine. Good. And then we get to kind of draw the picture that I drew by hand here. The test statistic, remember here, is going to be past the critical value. So the critical value is this red line here. That's at positive 1.645, but that's the critical value. Okay, but the test statistic is 2.17. I need to slide this to go up past 2.17 right there. Okay, so again, the pink area is alpha. That's clearly bigger than the blue area, which is my p-value, 0.0150. Okay, and so again, whenever this test statistic goes past the critical value right here, then the blue area, which is the p-value, will be smaller than the pink area, which is our alpha. So I could say that the p-value here is less than alpha O, which was up here, 0.05. Okay, and whenever it's less, we would reject the null hypothesis. And in this case, let me just be a little more careful here. I'm going to actually state what the null hypothesis said. It said up on the top here that P was 50%. So we're rejecting the statement that it's 50%. We are supporting the alternative. So supporting H1, which had said P what? Was greater than 50%. Okay, so I'm going to pick a conclusion that says we support the claim here, H1, the claim that the proportion of, I think, Mac users that are politically liberal is greater than 50%. So I think that's what we'll be answering shortly here. We rejected the null hypothesis and supported the alternative, right? Reject HO, support H1. And the data support the claim that a majority, that's the more than 50% claim, of Mac users are politically liberal. That should be fine. Okay, so that's that one. Okay, so now we're going to do one more. I'm going to jump up to question 6 here. And it's just another hypothesis test, but this one again won't have any step-by-steps other than a whole bunch of questions you have to ask, one at a time. So it says in Mendel's famous P experiments on heredity and genetics, among a random sample of 4,289, let me put that down. Pea plants, 3,157 were observed to have yellow peas. I think that's the color of the flower, but honestly I don't know. The others were green. His theory claimed that yellow peas were dominant over green, so 75% of the offspring between green and yellow should have yellow peas. Test the claim at 2% significant. 2% significance, so alpha is going to be 0.02. That the proportion of all such peas is equal to 75%. That sounds like a null hypothesis. P is 0.75 against the alternative that the proportion is not 75%. So P is not 0.75 here. Okay, so let's see here with Q, we can go ahead and do our Q here. That's 1 minus P, so the complement of 75% is 25%, 0.25. We'll need that. We'll need our P hat value, so that's X over N, 3157 over 4289. So let's see how that comes out. So 3157 out of 4289. Okay, so 0.0736 with three significant figures here. 0.736. And Mendel's theory predicts 75%. So we almost got, we got almost 74%. That may be within the margin for error of 75%. So that's obviously why we need to run the test. Okay, so now we can go ahead and do our check here. Oh, by the way, I guess we could enter some of these values. Remember, when your alternative hypothesis here says not equal means less than or greater than. So I just wanted to note here that this is going to be a two-tailed test. And I think we could probably put some of the numbers in here. So for the null hypothesis, we'll say P is equal to 0.75. And for the alternative, we'll just pick the right one. So this should be not equal to 0.75. And this is a two-tailed test, we've already decided. Okay, so at some point, we're gonna need to do our P hat value. We did it up here, so I guess that's good. N times P we need to do, so N is 4289 times P, that's 0.75, and NQ 4289 times 0.25. Okay, so we'll run those. So 3216.75. And all it needs to be is greater than or equal to 10. Obviously, we're good there. And then the same computation times 0.25 though. 4289 times 0.25. Looks good. So that comes out to be 1072.25. And of course that is also greater than or equal to 10. Both of those need to be greater than or equal to 10, so we'd say check, we're good to go. So let's go ahead and put that in real quick. So NP 3216.75, NQ 1072.25. Obviously both greater than or equal to 10, so yes, the criteria are satisfied. If I could just, there we go. Okay, so we're good there. Now we already did our P hat values, it's 0.736. There, and I'm gonna check it. Okay, that's good. So then the next thing is the test statistic. So the formula's here. It's P hat minus P over whatever. So P hat was 0.736. P was almost the same, 0.75. Is that significantly different? I don't know yet. Okay, over square root PQ, that'll be 0.75 times 0.25 over n, which was 4289. We'll see how significant this comes out. Okay, so now I unfortunately have seen a little problem here. If you notice, I had a 0.737 here that I have just repaired to a 0.736, which was the correct value. So I'm going to go ahead and use that correct value here as I compute the test statistic. So 0.736 minus 0.75. Okay, over, now square root, fraction. All right, 0.75 times 0.25. Over 4289, looks good. And let's see how it comes out. All right, so this is negative 2.117. We'll call it negative 2.12. Right? Yeah, negative 2.12. Okay, so let's put that in and keep our fingers crossed. Looking good. Okay, and now just the kind of testing for significance now. We need that alpha value, which is the level of significance. We've already said it was 0.02. And the critical values. Now this one's a two-tailed test here. We've denoted over here. And so we need to look up a negative and a positive critical value from table A2. So let me go ahead and slide up to that. Again, it's a 0.02 and a two-tailed test. So here we're starting with the critical value. Again, our alpha is 0.02, but again, we're looking it up under two-tail this time. Okay, just the bottom row where all the z-scores are. Right here, 2.326 is the z-score. That'll be plus or minus because again it's a two-tailed test. So I'm going to put two critical values, 2.326 and negative 2.326, like that. Okay, that's the z critical value and the negative z critical value. Okay, and so we'll put those in. Like that. And then you're asking yourself, and I think I'll check these. Those look good. And so then we're asking whether our statistic, our test statistic, is significant. So I'm going to circle here and point out that it's negative. So it's negative 2.12, which will be just not quite as extreme as the 2.326. So this is not statistically significant because it's not in the tail. So what you're saying here is, Mendel was claiming this null hypothesis that 75% of the P's should have come out yellow, I think. We got 73.6%. That is different, but it was not significant enough to say that Mendel was wrong, is the idea here. So we'll be supporting, we won't be rejecting what Mendel claimed. Okay, so now, so that's the critical value. Got that all set up. It's not significant, so no. The z statistic indicates the sample proportion is not significantly different from the assumed population proportion. I think that's what we're saying here. And so now a p-value. So let's go ahead and slide down here. This time our test statistic is negative 2.12, so I'll go ahead and plot it down here. Okay, that's our z-test statistic. Okay, remember there's also a positive 2.12 on the other side. This is a two-tailed test. And we're trying to find the probability of being at least as extreme. So the extremeness is 2.12, but in either direction on a two-tailed test. So you're really counting both tails. But bottom line is, if I look up that negative 2.12 on table A1, let me go ahead and mark this down. I'm going to go down to negative 2.1 and over to 0.02 here on table A1. Okay, so we're going down to negative 2.1 and 0.02. So you can see here that the area to the left is 0.0170. All right, so we'll go ahead and put that in our notes. Okay, so down here we noted a 0.0170. Okay, so that's the area on the left. I'm going to go ahead and shade these real quick. So we have a left tail and a right tail. It's a two-tailed test. Okay, so each tail is 0.0170. So the p-value is going to be twice that. So I'm going to write kind of small on this one to squeeze it all in. So for the p-value, I'm going to write 2 times 0.0170. So let's do that over here. 2 times 0.0170 is equal to 0.034. I'll go ahead and just say 0.0340. Okay, and remember the alpha was 0.02, so this is bigger than 0.02, which is our alpha. And now I want to remind you, when we compare these, you don't really need to look at you only need to look at the first 2 digits. So I like to obscure the second 2 digits like that maybe. And so we're just seeing the 0.03 bigger than or equal. Technically the rule is greater than or equal here. But because it's greater than or equal, greater means that we fail to reject HO. Which said that the proportion was 75%. Okay, and we don't support the alternative H1, which had said the proportion is not 75%. Okay, and then what we want to do is just try and find a conclusion that kind of fits this. Let's go ahead and put in our answers here. So the p-value is 0.0340. Okay, hopefully that's right. And then we'll do our slider to compute it. This one just automatically doubles the area for us. So our z statistic was negative 2.12. I'll just you have to grab the dot that's black here. There's not a dot on that side. Just make it negative, so drag it over this way. And so we want to make it negative 2.12. So that's a ways down. And a little trouble here. There we go. 2.12 right there. And so the area beyond that test statistic's 0.0170, which is what we got, but it's doubled that area, 0.034, which is what we got here. And so everything seems to be working out just great. we are failing to reject the null hypothesis. Okay, right here. And then we want to choose the best conclusion. We can't reject the claim. We never support the null hypothesis here. So Mendel was saying that the proportion is 75%, and we are unable to reject that. So I think that's probably a good way of saying it. Don't say that Mendel's right, or even that we support him. It's just that the data that we have here is not sufficient to reject it. So based on the evidence, we cannot reject the claim that it was 75%. That's failing to reject the null hypothesis. Okay. And that's it.